This is our 5140 project. Today we're talking about the effects of wildfires on global climate and health. The motivation for this project was during the summer of 2023, wildfires in Canada deposited particle matter into the atmosphere, and those particles were visible even in Columbus, Ohio, weeks later. Think about like the air quality index was 400 in New York, I believe. That was when everybody was going out in the summer and you just couldn't see anything in front of you because the sky was just not the right color. This sparked our interest in the overall effects of wildfires, both on how they affect the climate as well as how they affect our health as humans, like how all the particles can give you headaches or mess with your lungs and stuff like that. There was an article written by the New England Journal of Medicine, which talks about how the wildfire season is now starting much earlier and ending much later due to the effect of climate change. It also talks about how the forest loss in tropical areas due to wildfire damages, it damages the Earth's ability to absorb carbon dioxide and cool down the climate, which then also makes global climate change even worse. It also talks about how the primary air pollutants from wildfire smoke are normally particulate matter. So just some examples of wildfires. There have been 33 large wildfires this year, and they've burned roughly 386,575 acres across 10 states. On the left is the Canadian wildfires that I was talking about that happened over the summer, and on the right is a picture of the Maui wildfires that just happened recently that I'm sure everybody's heard of. The objective for this project, there was a few different objectives that we would like to study. The first was to see how much the wildfires affect the overall oxygen content in the air. Wildfires obviously burn many trees as well as release particles into the air, so inherently the oxygen amount will be lower due to the trees burning. The group would also like to see how much the fire impacts initial oxygen levels as well as the long-term oxygen levels. We would also like to find out how the fire affects the ozone layer. Particles from the wildfires have the ability to set off a chemical reaction which can erode the ozone, thus putting people in danger to increased UV radiation. We would finally like to see how much the CO2 and particulate matter affect the condition of the air and climate change, both for human health and for the health of the world in general. We would like to see the magnitude of the effects of the particulate matter and CO2 based on the fire size. The activities we're going to conduct. First, we would like to measure the oxygen change from a fire, first getting a reading at ambient air before any fire has occurred. This will be done using an oxygen meter. After the ambient oxygen levels are measured, a simulation forest fire will need to be run because we're not trying to burn an actual forest. The oxygen levels will be measured in 3 different sections of the fire. So initially it will be taken beforehand. Once will then be taken during the fire, and once will be, we will have it during the fire. Once will be as soon as the fire is initially put out, and then once a year later to see the long-term effects of the fire on oxygen levels. This will help show the cumulative difference in the oxygen levels because of the fire. After this is done, another simulation will be run with a different size fire, which can either be much larger or much smaller, just depends. The same test will be run for this fire, which will give us insight on how much the size of the fire actually affects the oxygen levels.
The device that we're going to use to measure oxygen levels in the air is the oxygen meter PCE DOM20. This is a measuring device to determine the oxygen content in both liquids and in the ambient air. With this oxygen meter, water analysis can be carried out, for example, on the oxygen content in a very short amount of time. And with the integrated temperature sensor, the oxygen meter is able to carry out an automatic temperature compensation. As a result, this oxygen meter is also used for analyzing the oxygen content of lakes or streams, as strong temperature fluctuations can occur there, which would falsify the measurement result. Strong temperature fluctuations are something we're going to have to deal with in wildfires, depending on how close we are with each measurement. When we're taking 3 measurements, we're not going to have the exact same temperature every time. This device does require some calibration before we start testing. So before the initial startup, the sensors on the oxygen measuring device are initially dry, and in order to carry out a measurement, the sensors of the oxygen measuring device must be filled with the electrolyte solution that comes with it. For the first measurement, The device must be calibrated in fresh air before we can move it in to the wildfire location and measure. Once calibration is complete, the device should display a measured value between 20.8 and 20.9% oxygen. The Teflon diaphragm is capable of allowing oxygen molecules to pass through it, which is the most important component of the device, as it is how the oxygen meter can measure the oxygen in the air. This device is relevant to the experiment because this is how we're going to be able to determine the different oxygen levels in the air before the fire, after the fire, and in subsequent fires, to observe the effects of these fires on oxygen concentration.
So the second test that we need to run is the test for measuring the overall ozone. Now this test is going to be much similar to that of the oxygen test. The ozone levels will first be measured in ambient air condition as a test. Then the 2 simulation fires will be run, different sizes of course, and readings will be taken during, immediately after, and then a year later. The reading found a year later, will be specifically important due to the importance of the ozone layer in protecting us from UV radiation. If the ozone does not heal over time, then these fires can have a devastating effect on human health, as we can start being impacted by much more UV radiation over time.
The device that we're going to use to measure UV radiation and ozone is the Dobson spectrophotometer. This device can be used to measure both total column ozone and profiles of ozone in the atmosphere. The Dobson spectrophotometer measures the total ozone by measuring the relative intensity of the UVB radiation that reaches the Earth, and it compares it to that of the UVA radiation at ground level. If all the ozone were removed from the atmosphere, the amount of UVB radiation would equal the amount of UVA radiation on the ground. As ozone does exist in the atmosphere, the Dobson spectrophotometer can use the ratio between UVA and UVB radiation on the ground to determine how much ozone is present in the upper atmosphere to absorb the UVC radiation. The ratio is determined by turning the R dial, which can be rotated a full 300 degrees on the instrument. The spectrophotometer compares 2 different wavelength intensities, UVB, which is typically around 305 nanometers, and UVA, which is roughly 325 nanometers, in order to calculate the amount of ozone. When turned, the R dial filters and blocks out the light of the UVA wavelength until the intensity of the 2 wavelengths of light are equal. The ratio of the 2 wavelengths at incidence can be calculated once the filter intensities are the same. The results are measured in Dobson units equal to about 10 microns of thickness of ozone compressed to standard conditions for temperature and pressure in the column. This tool is going to be very important as it will help us analyze and compare the effects of wildfires on ozone levels in the atmosphere.
The final test, and arguably the biggest test that we will have to run, is the problem that comes from wildfires with the amount of particulate matter and carbon dioxide that is released. These tests will once again be similar to the previous ones for the oxygen test and the ozone test, and that we will run 2 fire simulations of differing sizes, and the readings will be taken in similar fashion. 1 time before, 1 time during, 1 time immediately after, and 1 a year later. These measurements can then be used in direct correlation with previously found data to assess the overall risk to human health with things such as the air quality index. One example of this can be seen with the air quality index, which was particularly bad after the Canada wildfires this past summer, as I was saying earlier, with the very high levels in places like New York, even here in Columbus, and places like Akron.
This device might be a little familiar to most people in this class. The Temtop M2000, second edition, air quality monitor. Relevant equation is going to be Gaussian plume model that we've studied thus far in the semester. This device is a handheld air quality monitor that's going to allow us to measure not only PM10 and PM2.5 levels in the atmosphere, but if desired, carbon dioxide, temperature, formaldehyde, and humidity. For the purposes of our experiment, we're only concerned with PM10 and PM2.5. To operate the monitor, the power button must be held for a few seconds and the monitor will turn on and begin to initialize. After about a minute or so, a menu will pop up that shows the available things that it can measure. Select PM. Once you select it, levels are going to be measured by using a laser sensor in the device. You can measure it for as long as you want to. It'll just read until you turn it off. This device relates to our experiment because it allows us to see the levels of particulate matter during a wildfire, which is probably the most visible component and most something that people associate with wildfires is the blocking of vision and the haze. The important thing about this device is that it's going to allow us to compare those values to the air quality index and assess the impacts on human health.
As Jackson mentioned about how we're going to collect the data, the atmospheric particulate matter, carbon dioxide, oxygen, ozone layer levels will be monitored year round in areas where there are commonly wildfires and not, before, during, and after. The data collection will also then be compared to previously collected data and historical data to help see what's actually happening with the fires. Our expected results for atmospheric oxygen is going to go down. So currently there's 21% oxygen by volume in the air. However, due to deforestation and burning of fossil fuels, this level has been a slow decrease over the past couple of decades, as you can see in the chart on the bottom. So we expect the results from the fires to go down because the oxygen itself will be consumed during the burning process, as well as after, due to the lack of plant life being able to create additional oxygen through photosynthesis. However, about a year or two after the fires, new vegetation will be growing back, which will help stabilize the oxygen levels. So our expected results for the ozone levels is they'll go down, but they should bounce back. So this past, in 2021, I believe, there was large forest fires in Australia, and they saw that between 3 to 5% of the ozone layer was depleted in the southern hemisphere. However, it was able to heal itself in about a year. So we expect similar results to come from our data. So what causes the ozone to be depleted is the wildfire smoke breaks down the hydrochloride in the lower stratosphere, which generates chlorine monoxide, which according to MIT is the ultimate ozone depleting molecule. So our expected results for particulate matter is, as you can expect from what we saw this past summer, to be extremely high during and right after the fires. So according to the US EPA, particulate matter is about 20% of the atmosphere during these forest fires. So we expect to see extremely high concentrations, such as New York, when they saw 117 micrograms per meter cubed. So at the end of the year, after we've collected our data, we expect the particulate matter to somewhat return back to a safe or normal level. Our expected results for carbon dioxide. So we expect it to skyrocket where fires are taking place. The increase will obviously vary depending on the size and duration of the fire. So for example, in 2021, 1.76 billion tons of CO2 was released from the burning of boreal forests in North America and Eurasia. However, it's estimated that about 80% of this CO2 is actually recovered by vegetation regrowth in the coming years. So really only 20% of the total CO2 being emitted by these wildfires is contributing to climate change. So our implications for stakeholders. So as you guys probably know, there's really nothing we can do to prevent forest fires. However, there are some measures that we can put into place and do to prevent these extremely large forest fires from wreaking havoc. These are such as fire breaks, which is where the vegetation is removed and natural barriers are created in order to stop wildfires from continuing. You can see a picture of one of these fire breaks on the bottom left. And then another good solution or measure to prevent such large fires it's called backfires, which is where firefighters deliberately start fires in front of the active wildfires. And this will consume all of the debris and brush and the fuel for the fire before it can make it to where they've burned. This helps stop or divert the fire from houses or just in general. You can see a picture of that on the bottom right. As for recommendations for the people around the wildfires, we believe that the best solution is to completely remove yourself from the area, go out of town, visit relatives, do whatever, just stay away from where the air quality is super poor. But if that's not an option, your next best option is to stay indoors and try to prevent breathing in the polluted air. And that concludes our presentation for the first project. Thank you.